In this example, the problem that we're going to be looking at is we've been given a linear transformation. T of x1, x2, x3 is the following set of three linear combinations. 2x1 minus x2 plus 4x3 for the first component, x2 minus x3 for the second component, and 5x1 minus 2x3 for the third component. So first thing to observe about T is that T accepts an input in R3 and gives us an output that is in R3 as well. Now, that's going to be important for the questions that we're posing here. So the first question is T 1 to 1? Now, T is 1 to 1 implies that if the images of two vectors are equal, then their pre-images will be equal as well. So T is 1 to 1. Is equivalent to saying that the null space of A, or the null space of the matrix associated with this, is the set that contains only the zero vector. Also equivalent to saying that the nullity of both T as well as A is equal to 0. We want to make sure that this thing has a zero-dimensional kernel. So with that in mind, normally what we would do is say take T of x, set it equal to the zero vector, and solve for the x variable. So first thing we want to do is set up what the matrix of the transformation is. Now the matrix of the transformation, as discussed in section 6.1, we can read each of these entries from left to right, and each one of those will represent a row of the matrix. So the first row will be 2x1 minus 1x2 plus 4x3. That's 2, negative 1, 4. Second row will be 0, 1, negative 1, based on the coefficients that I see. And the third row will be 5, negative 2, 5, 0, negative 2, excuse me. And again, we'll be augmenting that with the zero vector. Taking this down to reduced row echelon form will let us know what the kernel of this transformation is. So, turn into the old calculator, enter the matrix menu, edit ourselves a 3 by 4 matrix. First row will be 2, negative 1, 4, 0. Second row, 0, 1, negative 1, 0. And the third row, 5, 0, negative 2, 0. Taking this down to reduced row echelon form, tells us the identity matrix augmented with a column of zeros. So reduced row echelon form lets us know identity matrix augmented with a column of zeros, which lets us know x1 is 0, x2 is 0, and x3 is 0. So because there was no free variable associated with this, that meant that the kernel of T, which is the same as the null space of the matrix A that we just came up with, contains only the zero vector. As such, we can draw the conclusion that T is 1 to 1. Essentially what we just showed is that the pre-image of the zero vector is the zero vector. That uniqueness lets us know that it is in fact 1 to 1. Now as far as onto is concerned, we would be checking the range of T. So if the range of T is equal to the codomain in this case would be the R3 that we referred to back up here. If that is the case, then we are good. So what we're going to do is find the dimension of the column space. So the rank of T, that's going to be equal to the dimension of the column space of A. However, we already know that reduced row echelon form of A from the previous part is the 3 by 3 identity matrix. Now, to get the dimension, we count the number of columns that contain a leading 1. Well, there's 1, 2, 3. So the dimension of the column space of A, which we define as the rank of T, is equal to 3. Now, that 3 matches the dimension of the codomain. So So the dimension of the codomain is equal to 3. And the only way that you can have a subspace of something with the same dimension is if they are equal to one another. So this implies that the range of T, which is the same as the column space of A, is equal to the codomain. As such, we can draw the conclusion that T is onto. That takes us to our final one, which is T an isomorphism? The answer is yes. An isomorphism is what you get when you take something that is both one-to-one and onto. So because the answers for part A and B were yes, it is one-to-one, and yes, it is onto, then yes, T is an isomorphism.